Where am I? Right here.
Yeah, you look good. All right. So the talk is entitled Close Encounters of the Higher Kind, Emulating Constructor Classes in Standard ML, and Yutika Nagashima is going to give the talk. Here.
Thanks. So I started using ML in 2013. And soon I realized that the community of functional programming languages isn't really large. And what's worse, I feel like that this community is strangely divided. Haskell users prefer type classes to module systems. ML users do have a proper module system, but not so many of us use the abstraction type classes provide. Haskell users prefer lazy evaluation, and ML users tend to prefer strict evaluations. For some reason, I feel like that we also have different preferences over proof assistants. Not really, actually. Yeah, so today actually I realized that many OCaml users prefer Coq.
And some Haskell user like Isabelle, which is also a very good proof assistant.
Oh, really? Thank you. I will tell it to Gawin. Okay, and workshops take place in parallel, making it hard to exchange ideas across languages. Okay, so this divide is kind of understandable. Different people prefer different things. And I personally like strict evaluation, and I enjoy using module systems of ML. But at the same time, I don't want to give up the benefits Haskell users enjoy. We already know that we can emulate lazy evaluation within ML's strict evaluation to some extent. We also know that Haskell's type class and ML's module system can be used for similar purposes. Today, I talk about how to emulate constructor classes within ML using ML's module system. So maybe some young people are not familiar with the word constructor class. Constructor classes are class mechanisms based on type constructors, such as list and option. Famous examples would be monad and applicative. So the subtitle of this presentation is Emulating Constructor Classes in Standard ML. To be more precise, I'm talking about how to do that without changing the language. Why am I emulating constructor classes? I have 3 reasons. First, I wanted to prove proof automation in Isabelle using monads and monad transformers. Second, I wanted to reason over classes rather than concrete type constructors so that I can change which type constructor to use later without agonizing pain. And third, I wanted to avoid manually writing commonly used functions such as for them. Okay, ML doesn't support constructor classes natively, so I emulate constructor classes using ML's module system. So for this talk, I have 2 take-home messages, one for ML users and the other one for ITP users. For ML users, I talk about how to emulate constructor classes in standard ML. I didn't change the language, and I didn't use any dialect-specific features. So if you use any ML dialect with a module system, you should be able to use it in your system. So this is a workshop on MLs. I shouldn't spend too much time explaining how I improved Isabelle proof automation, but if you are looking for a better proof automation tool, please look for my proof automation tool called Proof Strategy Language on the internet. It's easy to use and it's easy to install. Okay, so to be fair, our work is not the first project that try to bridge the gap. I mean the gap between Haskell-style class mechanism and ML's module system. Stefan Wehr and Manuel Chakrabarty first introduced an approach to implement type classes in using MS module. And later, others also tried to bridge the gap, mainly by extending the language. The biggest difference between the approach and ours is that we didn't change the language and we are not using any dialect-specific features. So let me explain how I did it through an example. So here we have the minimum specification of monad, which has one type constructor monad and two functions, return and bind. On the other hand, the full specification of monad has lots more. It has lift m, filter m, fail, forever, join, and so on. But the good thing about our library is that users only have to specify the minimum definition of that constructor. So in this case, I provided two functions, return and bind. And once we have instantiated monad list as monad, we can apply this ML functor called makeMonad to generate the full-fledged instance of the list monad. We can do it automatically because we can define all the auxiliary functions in the full specification using the minimum definition. And the elaboration functor makeMonad is only half of the automation we achieved. The other half is about automatic instantiations as superclasses. We know that every monad is applicative. So we can safely include the specification of applicative inside the specification of monad. The keyword sharing ensures that we are talking about the same type constructor. We have an ML functor that generates the minimum definition as applicative out of the minimum definition as monad. And we do this recursively. This figure shows the hierarchical relation of three constructor classes. Functor is a superclass of applicative, and applicative is a superclass of monad. Once a user provides the instantiation as monad, meaning our library produces the minimum definitions as applicative and as functor. And for each minimum definition, we apply elaboration functor. And interestingly, I think this framework should be extensible. I mean, you can provide or you can extend, for example, monad by providing your own module's signature and elaboration functor. The situation becomes more interesting when we talk about multiple inheritance. So here, monad with 0 and plus is a child class of both outer and monad. But fortunately, our library is based on statically known mathematical properties, so we can manage to avoid the so-called diamond problems. In this example, if you have an instantiation as monad with 0 and plus, it doesn't matter semantically through which path you inherit the methods of applicative, because in any case, they have the same properties. Okay, how is our approach different from Haskell's constructor class mechanism? Haskell defines the return of monad using the pure of applicative. In our approach, we go the other way around. We define the pure of applicative using the return of monad. This is how we implemented the automatic instantiations as superclasses. Okay, let me compare our project with other two projects. Stefan Wehr and Derek Dreyer discussed how to implement type classes in ML modules back in 2006. Interestingly, back in 2006, Derek Dreyer already discussed that they can extend their framework to constructor classes. In fact, we did implement our library in a similar way. While Stefan Ware discussed that his approach can't handle construct classes. Neither of them discussed about automatic instantiations as superclasses. And Stefan Ware did discuss that it's not his approach can't handle default definitions. We did address this problem by introducing using two signatures for each constructor class. He also discussed that his framework can't handle recursive type constraints such as this. We addressed this problem by using ML functors. What we do not have in our framework is the implicit typing scheme. With our library, users always have to make it explicit to which constructor each method belongs by adding a qualifier or opening the module. Okay, I talked a lot about ML, and now I want to talk about how I improved proof of automation in Isabelle. In Isabelle, when we prove theorems, we apply tactics. Tactics are functions from a value of type them to a lazy sequence of values of them. The type them represents both proved theorems and conjectures with proof obligations. If your conjecture still has a proof obligations left, they appear as proof assumptions of implications. And interestingly, or importantly, you can see that tactic admits non-deterministic choice. The return type of tactic is not just the type them, but it's the lazy sequence of thems. We can also combine multiple tactics using tactic combinators. In this example, I combined three tactics, tactic A, tactic B, and tactic C, using the sequential combinator then. Each of them can be a combined tactic as well. Here, I combine tactic A1 and tactic A2 using the non-deterministically using the append combinator. So let me illustrate how this tactic might work using an example. So let's say you have a conjecture Px and apply this combined tactic. First, it applies tactic A, it returns something, and it applies tactic B to the result of tactic A. And it applies tactic C to the result of tactic B, but it fails, returning an empty sequence. So it backtracks to the result of tactic B, and it fetches the second element. And it tries to apply tactic C, but tactic C fails once again, returning an empty sequence. For the sake of argument, let's say tactic B returns exactly 2 elements. So even though we backtrack one step, we can't get one more element from tactic B, so we have to backtrack one more step, and we get the second element from tactic A. Then it applies tactic B to the second element of tactic A, and this time tactic C succeeds, returning 1 element. And at this moment, Isabelle stops working without proceeding further. Now you can see that what we are doing in theorem proving is implicit tree traversal using the non-deterministic monad. We can make this proof search more powerful by making the size of the tree larger. But this also means that we have to wait for a long time. For me, it's okay to wait for a long time if I can get the proof automatically. But what I don't want to do is to wait for a long time whenever I check the proof. Once my tool finds a proof, it should return an efficient proof script that doesn't involve many backtracked steps. So I decided to trace the proof search using the writer monad. But Isabella already uses the non-deterministic monad, so we combined them using the writer monad transformer. This is how I implemented powerful proof search with efficient proof script generation. Okay, let me show how to use my tool. Oops. Can you hear me? Yes. Good. Okay, so can you read? I can't read. And
It's good.
good. For me it's fine, but oh no. Yeah, that way. Cool. Thanks. So I took this, actually I stole this homework from Sato University in Germany. So this is a homework assignment used for students. This file contains a couple of sorries. These sorries mean that, sorry, I can't prove this conjecture for now, but I believe that these are true. Students have to replace these sorries with proper proof scripts. So let me show how professional proof engineers write proofs. Isabella is good because it has lots of strong tactics. For example, auto looks bad. Yeah, it failed. Isabella is good at simplifier, usually. And Isabella has a good subtool called sledgehammer. So when you type sledgehammer, it tries to offload the proof search to external theorem provers. And many of them are first-order theorem provers. And actually, I know that this doesn't work because it still has some problems about mathematical inductions. So this proof probably involves some sort of mathematical induction. So I say apply induct, and I got 7 sub-goals. Then I apply auto. I still have 7 sub-goals. Maybe I should give more hints to Isabel, like apply induction on A1. Now I have 4 sub-goals, and it discharges 2 of them, but I still have 2 sub-goals left. I think it's good time to give up. So I gave up to write tactics manually, and instead of writing tactics manually, I wrote this strategy. This strategy says that, hey, Isabel, make lots of variants of induction tactic at runtime, and then apply auto to the result of induct. Then check if there is a proof obligation left or not, and if there is a proof obligation left, backtrack to induct and apply different kind of induct method, tactic. And I can apply this strategy using keyword proof, find proof sum induct. So as I said, I'm fine with waiting for a long time if I can find the proof automatically. And I'm not sure how long I have to wait this time. I think we have a time for small talk. Do you have any questions so far? It's finished. Cool. Yeah. So now it returns this proof script, and if I click here, yep, it says no sub-goals, and we can say it's done. And we can remove the sorry. Now you can see that even though find proof took a bit of time in the beginning, the resultant proof doesn't take much time, and we can remove this. Cool. So this is my tool. So today I talk about how to emulate construct classes inside ML modules. To avoid code duplication, we defined 2 module signatures for each constructor class. And as usual, I defined monad transformers using ML functors. Oops. It's not presentation mode. Any questions?
We have time for questions.
Did you ever find any use for higher order functors?
Sorry?
Did you ever find any need for higher order functors that you could use?
I don't understand.
Did you ever find any need for higher order functors that didn't have a standard ML?
Ah, I see, I see. So I didn't feel the need, but I guess it's gonna be better if I had one. And probably I can implement implicit typing scheme using higher order functors, but I'm not completely sure. Yes?
Your automation library, did you get other users to use it as well, or is it just you for now?
I received an email from somebody which is not me, so probably somebody is using it.
Any other questions? Okay, well, thank you very much. That is the end of the session.